Here is Mr. Colin Stolley with advanced Python debugging techniques using GDB.
Cool, thanks. Yes, this is should be a fun talk, I hope. So I'm Colin Stolley. I work at Sprout Social in Chicago. For sure, talk to me afterwards. We are hiring, and if this kind of stuff excites you, I have some really nice people for you to talk to later. Also note that all this stuff is on GitHub, and it actually might even be helpful to pull it up and look at it. So sorry, there's no better way for me to communicate that to you than just put it up there, but if you want to take a look, we're doing some examples at the end. Looking at the code might be helpful. So cool, so sorry, and I keep looking at the screen because I can't pull the screen up on my laptop, so sorry, this is kind of awkward, but so typically when you have bugs in your code, your program's going to crash. That's kind of the happy scenario. Yay, I got a crash, I can fix it. It's easily fixed. Unfortunately, many times I'm not that lucky. My code has bugs and I don't get a nice clean crash. I don't get an error message in the logs. It's just not working. And a lot of times these bugs are you only see them under weird circumstances, particularly circumstances that you didn't see while you were developing, or when you were testing your code in a staging environment. Almost always in production, and for some reason, always around 3 a.m., often on a weekday. So debugging these programs in these kind of environments is extremely difficult. What you typically have is log statements, print statements. A lot of times that can be very helpful. One of our other developers, Jess Unrein, gave a great talk yesterday on logging and how important it is, and that's exactly true. Having good logging is helpful. PDB is another great tool to use for debugging Python programs, and remote debuggers, same thing. These are all helpful tools. However, all these tools require you have to have instrumentation in place before the bug occurs, and the bug has to be readily reproducible. What I mean by that is you have to have log statements in place in advance before the bug occurs in order to catch it, right? Or at the very least, you need to have a bug where you can do something, make the bug happen, and sort of dig into a little bit more. Many types of bugs, at least the kinds of bugs that I've confronted, this is actually not feasible, right? Because if I had known the bug was going to be there, I would have just fixed it, right? These always take me by surprise. So we're going to look at GDB as an option for debugging live processes that haven't been instrumented. What we want to do is attach to the process, see what's going on, and sort of catch these things in the act. The beauty of GDB, of course, is that you can attach to any running process. It could even be a Java virtual machine. It could be a Go program. Or in our case, what we're looking at today is the Python interpreter. The beauty of GDB 7 is that it actually has built-in integrations that enable you to actually directly go into the Python code, not just at the C level where we're typically used to seeing in GDB 6 and before. Actually, GDB 6 did offer some really helpful macros in a file called GDB init in the CPython repo. You can still use those if you're a GDB 6 person, but the integration in 7 is much better. And it's actually also more reliable. There's always a rub. The rub, of course, you have to have debug symbols. So the deal there is, in order for the debugger to know what's going on, you have to have a wealth of metadata in there to inform it as to what the state is. These debugging symbols are generated by the C compiler at compile time. The problem is, of course, that in probably 95% or better of Python installations out there, these symbols are stripped out. I don't fully understand why that is. I think it's probably to conserve bandwidth. In the day and age of terabyte hard drives, I don't know why we're worried about disk space, but perhaps to conserve bandwidth, we strip them out. Typically, they're embedded in binaries. They can also be stored in external files. And so you can get a hold of these things by either, so the -G flag on GCC, if you're compiling a C program, just toss that -G in there, it'll give them to you, just embed them right in the executable. You can also apt-get them. So specifically in the case of Python, if you're doing an apt-get, Ubuntu or Debian style, that's the Python DBG. You'll see a lot of those actually, I think, in the Linux distributions. These DBG this and DBG that. These are all just the debug symbols for these C programs to facilitate this kind of debugging. And likewise, if you're a Red Hat person, yum install, debug info, same idea. You want the debug symbols for both the C library, the libpython library, as well as the executable for the Python interpreter. So, likewise, if you have any C extension modules, you want to do the same thing. Toss that -G on there in the build step, so you have debug symbols there too. So that if you need to dig into the C extension, you can see what's going on there too. If you don't have if you don't have debug symbols for your extension modules, it'll just kind of give you this relatively unhelpful, oh yeah, it's in some module, but I don't really know what's going on. And of course, if you're trying to get at something, that's not very helpful. A couple other notes. I use OpenBSD a lot, so I have to set this little syscontrol thing for global ptrace. That's a security feature. We have something similar also in Linux for something called Yama. And this essentially, the idea here is you can't trace processes, even if they're owned by you, if they're not your direct descendants. And there's well-documented security issues on why that's important. People have been able to go into SSH and sort of attach to that process and then do cool things, or maybe nefarious things when using this mechanism. So it's typically disabled by default, but you can, of course, enable it. Be very careful when you enable it. As I just warned, there are definite exploits available for these settings, which is why they're turned off by default. So if you do end up doing this in production, at worst, set them back to disabled after you're done debugging. But yeah, they are definitely dangerous. Of course, if the process is running as a user other than you, you're going to need root. Simple as that. So this happens all the time. People ask me, okay, well that's great, but my production server is not outfitted with GDB, it doesn't have debug symbols, and furthermore, my DevOps team is never going to let me do this. So what can I do there? Or perhaps maybe the bug you're trying to chase down happens before you get a chance to install debug symbols or GDB on there. The beauty of this is, of course, if you can have a lab machine where the lib and binary versions are the same, you can actually drop a core on your production machine, copy that core file to your laboratory machine, bring the core file back up on your laboratory machine, preserving the state, and then debug from that point without ever having to actually go on to production to see what's going on. And I've done this on a number of occasions simply because I can get on to get the core file, but I'm not going to sit there and debug the process while my production is sitting there hurting because the process is not working. Get the process running again, but take a snapshot of the state so I can debug it later. The one trick, oddly enough, if you do have a laboratory machine, you do this sort of core file dumping and copying, make sure your Python code is in there, and it's the same path it was on production. Otherwise, you get all kinds of weird errors and it won't make any sense. It's like, well, yeah, you kind of have to have your Python code there because the Python interpreter debug symbols do not contain your code, and nor do the core files. So yeah, once you attach gcore as your friend, you can just say gcore and then a file name, and it'll just dump it out for you. This sometimes doesn't work. I don't know why, but never fear, there's always another way. You can also send a sigquit or sigseg signal to terminate the process, as well as drop a core that way. So you can get around it in different ways. Something like that, perfect. Finally, you're also going to need python gdb.py. This is in your CPython. I assume if you're going this deep into it, you're going to have a copy of this, the CPython source lying around. Grab that module, you're going to need it. What that module contains, read it sometime, it's quite interesting. It has a lot of tools for basically all the implementation for all the Python-specific tools in GDB. And you're going to need that available so that those tools are exposed when you're in your GDB debugging session. I typically just place it in my virtual environment bin directory. You basically want it where the Python binary is living. I always use virtual environments, so it's easy enough to just stick it in there. If you don't really know where to put it, you can also just add a GDB init file that sources it. Works great as well. So just some basics, and again, I'm not assuming everyone here has used GDB before. C programmers probably use this all the time. Maybe a lot of people in here haven't. So we'll just talk about some of just the basics of like what this thing does and how it works. Getting a core file, I mentioned that already, gcore. For looking at backtraces, this is probably the most useful command I can tell you about today, and good old pybt. So what that's going to do is it's just going to actually run through a backtrace, and we'll go through some examples, and you can actually see how this thing works. But the idea is this is a Python-specific backtrace, and backtrace full will give you some additional state information for each frame as it gives you the backtrace. And then if you want to go to the C level for whatever reason, you can also use BT, which is just the standard GDB BT backtrace. But of course, it's going to give you the backtrace at the C level, not at your Python code level. And that's a pattern that you're going to see all over the place. Same idea here. If you want to walk up and down the call stack, pi up, pi down, the C analogs being up and down, same idea. Pi locals and pi print. The idea here is I want to take a look at the local variables that are defined. One sort of annoying limitation of pi print and pi locals is if you want to look at like an attribute of a local variable, like self.foo, you can't actually do that very easily with pi print. I've been searching to try to find a way to do that. If anyone knows of a way to do that, let me know. But generally, you can only sort of look at the base level objects in the local scope. Info locals and info args will also tell you, again, at the C level, what variables you're looking at. Typically not nearly as useful if you're debugging a Python program as pi locals and pi print, but those are there as well for inspection. This, finally, is extremely useful. PyList or list will give you the source code of where the debugger is currently sitting. Incredibly useful. Kind of surprised me at first that I could actually like literally pull up the source code and have a pointer as to what line it's sitting at. I do a lot of threading work, so I want to know what threads are available and what they're up to. Info threads will tell you all that information. Very useful. If I want to select thread 3, for example, simple as that. And gets direct traces for all threads. So sometimes when I'm debugging a process, I have 10 different threads, and I don't want to necessarily iterate through each one by hand. This one does it for you. I can get a backtrace of every single thread that's currently in the process. Another very useful command. So typically, it's going to look something like this when you're going about debugging this stuff. You're going to attach to the process with a PID. You're going to give it the executable so it knows where to load the symbols from. Then you're going to see what threads are available. You're going to pull a backtrace, and you're probably going to pop around at different threads and see what's going on. At least that's how it typically runs for me. Pretty simple stuff, maybe. So let's take a look at some examples. Now, I've simplified these for brevity, but these are actual code examples from production code, not necessarily at Sprout Social, although some of them have come from Sprout Social, but others of them have come just from places where I've worked and actual code bugs that exist. So hopefully we'll get some useful knowledge out of just like don't write code that does this kind of stuff in addition to finding out how GDB works. That's my hope anyway. So the first we're going to look at is something that we do a lot. These are HTTP pollers. We had a situation where we basically have a process that repeatedly fetches data from a bunch of URLs. This is a very common thing at Sprout. We're constantly pulling in data from social networks. We do this a lot. And just to increase throughput, we're going to use threads. Of course, threads are of limited utility in Python, as we all know. But when it comes to I/O, they're incredibly useful because you're going to have a lot of blocking, right, when you're pulling stuff off a network. So let's take a look at the code really quick. If I can pull this up. Just to kind of give you a sense of what we're up to here. So I hope this code is reasonably straightforward for us to see. The idea here is, again, we're setting up a thread pool. We're going to basically dispatch just a crap ton of jobs into the pool. And then each job is basically this fetch method. Fetch method is going to build a URL. It's going to do some timing calculations. But ultimately, it's just going to bottom out in this requests call. I presume everyone is familiar with requests. If not, it's just a wrapper around URL lib that's very convenient to use. It's doing a HTTP GET request there on the URL and returning its JSON. We log what happened, and then we return whatever it got. So that's pretty much all it's going to do. And the idea here at the end, so we're going to instantiate it. We're going to kick off, say, 40,000 or so of these jobs. And then as they're completing, we're just going to log them out, and this is what happened. So that's basically what the example code does. If you see the bug already, don't tell anybody. This is a surprise. So let's just take a look here. So I'm sort of mocking out the HTTP request in this case. I have, and again, it's probably on my GitHub, an example of an HTTP server that does bad things. So it's going to, maybe it'll drop a connection once in a while. Maybe it'll do something stupid like that. Maybe it just won't respond right away. These are, of course, the kinds of things that happen all the time in everyday life. But for the purpose of this demo, it's going to be particularly bad, right? So that we don't have to sit and wait for 3 hours for it to fail. So I think it's already running. If not, this will be hilarious. I think it's not running. All right, let me see if I can get it running quick. All right. Maybe we'll have liftoff here. All right, let's give this another shot. All right, so excellent. So it's at a pretty reasonable rate of speed here. We're pulling down stuff off of this this URL. It's going pretty quick. See the counter going up really fast. That's always good to see. Now what I'm going to do, if I get over here, I'm going to curl this crazy thing, and I'm going to say, okay, just let's make it busted. Let's just start misbehaving like crazy. And you're going to see that throughput kind of diminish. It's getting slower and slower. It's starting to get really sad now. Notice the request time is roughly about the same, about 100 milliseconds or so, I think, something like that. Getting pretty stinking slow at this point. Kind of hoping it'll die pretty soon. That's where we're headed. So while we're waiting, let's get the process ID. Good old pgrep. There's our process ID. Whoops. I have no idea why I can't highlight that, but so it looks like we're at a dead stop here now. So this actually happened. And I actually want to point out that if I curl the server is doing just fine, by the way. So yeah, I can curl it all I want. It's still responding. It's just fine. But our poller has completely seized up. Also note, if we look at top, you can't look at top. If you look at top, it's doing nothing. It's just sitting there. Well, virtually nothing. So something's going on, right? So let's see if we can find out what's going on. So what's that? Oh, sorry, that's what. So let's go ahead and fire up the GDB debugger here. We'll go 13. What is it? 829 or so. Cool, so what just happened? We attached to the Python interpreter process. It traced through all the libraries that it linked in, loaded the symbols. So now we're pretty much good to go here. Right off the bat, we're sitting in receive from, so some people should maybe start to think maybe this is a network issue. We'll go ahead and fire off PyDBT and see what's happening. A lot of stuff going on here. Let's see if I can page down a bit. We'll get a little bit lower into the code. Again, this is all a Python backtrace, right? This isn't C-level stuff. So I want to make sure that's clear that this is an actual stack trace of Python code, not C-level code. Now, what we're actually looking at here, let's see if I can highlight it. So this is where we're sitting. We're making the GET request, and obviously nothing is happening. We're actually in our, let's see if I can find it. Here's our example 1 code, line 24. We're sitting here waiting for the request to come back. Okay, so let's take a look at info threads. See how many threads we have going right now. We have several. Thread apply all, PyBT. And what you're going to see, I know there's this is like an entire wall of text here. But what you're going to see over and over again is that every single one of these threads is sitting in requests.get, waiting for a response. Every single one. So now we could dig into this more. I kind of want to move relatively quickly here, so we'll sort of cut to the chase. But if we go back to our source code, and this is where audience participation gets fun, can anyone wager a guess? Since we're sitting stuck at this line, anyone wager a guess as to why? So this is actually one of the deficiencies of the requests API that I think personally, is the timeout is defaults to none. So there's no timeout on this at all. This will sit forever and wait for a response. Or in many cases, it will sit and wait for a read, or excuse me, it will sit and wait for a response. It may well fail on connection, but if it succeeds to connect but never gets a response, it will still wait forever for that response to come back. So what you have is you have a full saturated pool of threads all sitting here waiting for a response that they'll never get. It's very sad. So obviously, solution, specify timeout is a keyword arg. But by default, and I see junior programmers make this mistake all the time, there is no timeout. It will wait forever. And particularly in the context of something like this where you have a lot of activity, if there's a timeout, just fail. Don't sit and wait for it. But by default, that's what it does. So let's check out example 2. How am I doing on time, by the way? Okay, cool. So this is actually another very common thing. We have a queue of work that we're going to fill up. We're going to spawn a bunch of threads to consume until the work is gone. Pretty simple idea. So let's take a look at that code real quick. So we have a worker pool class, starting to look a lot like the other one maybe. Okay, so you've got a work queue and a result queue. We're going to pull jobs out of the work queue. We're going to do the work. We'll stick the result on the result queue. Excuse me. And then we'll return all the results as a dictionary. I hope that's kind of clear here. So we pull out the jobs. We add them to the queue. We fire off a bunch of threads, apparently 10. Those 10 threads, we'll start them up. We'll wait for them to finish when they're done pulling off work. And then we'll return the result. So this is just a little, kind of a work queue thing. We could have potentially used the thread pool executor here to avoid having to kind of implement some of the basics that it does for us. But we didn't, for whatever reason. Someone probably thought they were too smart enough to do it themselves. And then the other thing here, so here we're actually looking at the queue. If it's not empty, we'll pull off some work. We'll do the work. And then, of course, we'll put the result on the queue. So let's give that guy a shot. This one requires no. So it worked. That's good. Great. I'm glad it worked. Worked again. That's great. Let's try it again. That worked just fine. And it actually works fine a lot of the time. I'll bet you it won't fail today. Oh, it did. OK. So what the heck, right? You'd think it would be deterministic, but of course, when we're using threads, things aren't always deterministic. So we got a problem here, right? OK. So let's pop back to GDB. We'll take a look. We'll see what's happening. Look at Python. And oh, look at that. Example 1's still running. Isn't that something? All right, so So there's our PID. We'll give it the Python executable. We'll fire it up. Same thing as before. So let's get a stack trace. What's going on? So we're waiting on a join here. This is actually fairly straightforward, I think. This is actually waiting on all these threads to finish. Not terribly interesting. Take a look at info threads, see what else is going on. So there's only one other thread apparently running. So let's go ahead and look at that one. Thread 2. And we'll see what he's up to. So he's sitting here. Check this out. This is our little program. He's sitting waiting on workqueue.get. And apparently he's been sitting there for a long time. Now, let's have a look at PyLocals. Okay, that's not good. Live debugging for the win. All right. We're probably not. This is moving up and down the stack. Now, this is perhaps somewhat interesting. Let's move one more up here. But again, I want to drive home the point here that now we're actually walking through the call stack of the Python code. I realize this is a ridiculous wall of text. But the idea here is we're actually getting, here's the arguments for this class, this self. Here's self way up here. You can see my pointer. We have access to the result queue here, all tasks done. And of course, some of this stuff is unintelligible. But if we follow along here, I'd like you to take a look. And clearly, I've debugged this before, but for purposes of the demo, that's fine. Where are we at? Unfinished task 2000. However, I think that's actually in the result queue. But the idea here, I can't actually see it. Somewhere in here, there should be a unfinished tasks is 0. I'm just not seeing it because it's such an unintelligible wall of text. But the idea here is that we can actually take a look, if we're patient enough to go through the text, to see what's going on inside the code. And that's sort of the whole point. Actually, now that I notice it, here's work queue right here. So if we look here, whoops, that didn't work. We'll move down a bit. Max size. Anyway, that's fine. But the idea is that it's actually exhausted the queue. I really wish I could see where that thing is. It's in there somewhere. But the idea is that it's completely exhausted the queue, and it's just sitting there in get. Now, I don't know if anyone's familiar with the queue API, but if we go back to the code, I'm actually just going to. If we go back to the code, can anyone tell me? So we're sitting here, right? I think that's what it was. I should go back and double check. Yeah. So we're actually, let's just bring this home. PyList is telling us we're on line 32 here. There's our code. That's what's going on. So if I can actually get tmux to cooperate. So we'll go to line 32. So excuse me. So can anyone hazard a guess as to what's going on here? Yes?
It's a race condition. You check, then you get it on the next line, but the thread was suspended after it checked, and somebody else grabbed the job.
Exactly right. That's exactly right. So the idea here is that we are checking the queue if it's empty first, saying no. Then we go to grab a job, but oh, look, some other thread came in, grabbed the job before I got a chance to get at it. So now I'm blocking, waiting for the queue to empty out. And that's where I'm stuck. Excellent work. Thank you. So yeah, so that is yet another example. We'll try one more. I'm hoping we'll have enough time to cover all four. This is a CTypes issue. In this case, we are exposing some C functions to Python using CTypes. This was actually lifted predominantly out of PyChef, if anyone's used that. Not to pick on them, but I also haven't filed a bug report on this. Perhaps I should. Thanks. So let's take a look at what's going on there. Maybe, yeah. Cool. So this is your typical kind of CTypes thing. The idea here is we're just exposing some C functions and libcrypto to Python. And so CTypes kind of gives you the ability to wrap these things in Python objects and then call them. It's actually quite powerful. So we're setting up RSA size, private encrypt, generate key. There's probably a dozen other ones that I just simply snipped out for purposes of this demo. But the idea here, really salient point anyway, is we're just wrapping some C functions with Python so that we can access them. And so we have this little key class. Again, this is just adapted from what is actually in PyChef, but the mechanics are the same. So we can initialize it. We'll generate a key with this class method. We can encrypt stuff, just give it a value and some padding, and it'll just kind of figure that out. Again, all calling underlying C functions. That's all it's doing. And I just have some example code here just to sort of make that happen. So what happened in real life here was the Nops guy ran this stuff. He's like, oh, I got this great chef recipe. It's great. But look at that. I'm so skillful, I actually got the Python interpreter to core dump. I was like, very good, very nice. So why did it core dump? So again, GDB to the rescue, as you might have guessed. We can absolutely take a look at that. Just so we're clear here, we have the core file conveniently located right in this directory. So we'll go ahead and load that up with -c. Cool. Now, immediately, like right off the bat, don't even have to do anything, right? Take a look. RSA size, getting an argument, 0, hex 0. Then, let's highlight this so that we're clear. We're dereferencing a null pointer. Well, of course, we got a segmentation fault if we're dereferencing a null pointer. So right off the bat, we're like, oh, okay, cool. So this actually shouldn't be too difficult to debug. Good old PyBT, tell us what's going on. So inside our example, we're calling RSA size. That argument is apparently null or none. So I've kind of given away most of that just by running through that stack trace. We'll do a PyLocals here just to sort of expose the local variables. But again, key is equal to none here. So unsurprisingly, if key is equal to none, and we're calling RSA size on self.key, that's going to get a none, which is going to be a null. It's going to be a null pointer. It's going to blow up. So I've pretty much given it away at this point. But let's go ahead and just return back to the code. Oops. Or not. So what we have here is simply a failure to set key in the initialization. You have to call this generate thing first. And otherwise, you're just going to crash Python. So not too surprising there, nothing really that jarring. But to be able to pinpoint that error without having to wonder why the heck did. Generally, like when people see the Python interpreter explode like that, they start screaming and tears and things are involved. So very nice way to just immediately pinpoint what's going on. Finally, classic thread deadlock problem here. This is sort of a standard garden variety readers-writers problem. We have a pool of threads that might read or write, and we're going to use locks to serialize the writes. But we want to allow multiple reads to execute concurrently. So let's take a look at that code. And again, I hope this is reasonably reduced so that we can follow what's actually going on. So we have readers-writers. We have a write method and a read method. We grab a file lock. We write to the DB file. And then we just return the string write. For reads, we grab a mutex. We increment our reader count. We acquire the file lock if we're the only reader. do our read, and then likewise release it for the last reader to have the lock. So the idea here is if I come in and say, yeah, I'm a reader, I want to, if someone else has already got the read lock, great, we'll increment the count, we'll give you your read concurrently with everybody else, no problem. And then we'll log if anything bad happens. So I've basically just set up a test case for that. We'll instantiate the class, we'll set up another thread pool, we'll pass it, 50,000 or so test jobs to just write out. I am biasing this so that we're kind of read heavy, so it has a 2 out of 3 chance of picking a read and 1 out of 3 chance of picking a write. And we'll just submit those off to the pool using our read and write functions. And then we'll wait for them to finish and we'll log them out. And then we'll just rinse and repeat when that's done. So let's see how many more tmux sessions I can stack onto here. Ooh, that's crazy. Yeah, all right, we'll just reuse this one then. This is incredibly hard to do when you're not in front of the screen. Yeah, so let's go ahead and run that. And at an amazing pace, we're actually reading and writing, right? And it's pretty decent, no problems. So I'm going to cheat a bit. I'm going to create some problems. I'm going to make some I/O problems happen on the actual machine. So as long as nothing bad happens, this code works great. It's always when something bad happens that we run into trouble. So let's go ahead and run my little chaos shell script here, which is basically just going to pick at random times to just remove the DB file. Now, this sounds kind of silly, right? Just like deleting the database file out from underneath it. But in fact, in these days of clouds and iSCSI and hypervisor pauses and things like this, you absolutely can have a situation where the file might temporarily not be writable, or might just disappear, or maybe there's something else going on. So obviously, it's a little crude, but let's just go ahead and run it. And what do you know? You guessed it. It froze up. No stack trace, no errors, just looking stupid. That's all we have. So by this time, we're familiar with the drill. Let's take a look at GDB. If I can type the word pgrep. Getting quite a collection of stalled Python processes on here. 5717. All right, so let's take a look at the threads first, see what's going on there. Everyone's sleeping, so that's always fun. Let's take a look at where everyone's sitting right now. Waiting for a file lock. We're trying to write. We're waiting for the lock. OK, let me see if I can actually get up there. And this isn't like totally obvious. Yeah, waiting for the lock. Let's page up the next one. What do you know? Waiting for the lock. By this time, suspense is no longer a thing. Waiting for the lock. And finally, we have one that's apparently sitting here waiting for everybody else to finish. So what's going on? So we have a bunch of writers sitting waiting for the lock, but apparently no readers that actually are holding the lock, right? So with only a fraction of time left, let's go back to the code. Yeah, we'll kill one of this. Anybody care to offer a guess as to what's going on here? And we're very short on time, so I'm going to rush. I'll give you a hint. It's in this method. First of all, some dope made this at debug level. And in production, you're never going to use debug. So even if there was an error or exception, it wouldn't have been logged anyway. So that's bad. Don't do that. The other thing is here is that like if an exception happens, it's going to bomb out, and it'll never let go of this lock. And that's exactly what happened when I was screwing with the DB file, right? Is that like an exception happened, it never released the lock, everybody else gets jammed up. So Cool. So in conclusion, GDB is a sophisticated tool. I've scarcely touched the surface here. But this sort of gives you a flavor of the kinds of things you can do. And there's like way more sophisticated stuff you can do. I'm just trying to give you the sort of basics of what's going on. I would advise you to resist the temptation to restart and fix it later or blame it on ghosts or solar flares. This is what people do all the time. Oh, who knows? Just restart it. It's fine. Well, the idea is like we should actually find out what's going on when you have these crazy problems. You might learn new things, and you'll definitely improve your code. So that's my advice to you. Thanks a lot. Don't laugh. That's my Twitter handle, but I never post to it. But you can absolutely send me stuff. But yeah, it's like probably 3 years old. So yeah, thank you. Thank you for watching.